Yeah, this is different. Being blinded is a new experience. So I'm happily welcoming you. Hello, to our session, the first one that we have here in this biochar area. For everybody who hasn't joined yet, this will be very interesting. Especially if you're into the evaluation of resources that now are kind of not really looked at. This session will be about the carbonization of sewage sludge biosolids. So a very interesting feedstock for pyrolysis for the further use. I will not be talking about it too much because we actually have experts who know a lot more about this topic. I'm Harald from the European Biochar Industry Consortium, and I have the pleasure to be moderating this, also with Donata, my colleague, and she's a lot more into sewage sludge and policy, so I will hand over the discussion of the word to her. She will give a short intro, and after that we'll have some of the most renowned experts in this field in Europe from different companies, member companies of the EBI, who will explain a little bit how with their technology they handle problems that we do have with this feedstock, and also present very interesting solutions to agriculture, to materials, and to combat climate change. So very much looking forward to this. Thanks a lot, Donata.
So, good morning everyone, and bonjour à tous. Merci pour être ici dans ces pavillons pour démarrer cette expo.
Today.
Je suis Antakiari, the European Biochar Industry Consortium. Now I'll switch to English so that I don't humiliate my French father. And today I will present very quickly the EBI work on policy, specifically on sewage sludge biochar, and then I will leave the floor to more in-depth presentations on the topic. So EBI has typically 4 pillars of activities. We can see market intelligence, communication, industry standards, and policy. Policy arises as a key aspect for EBI work, and this focus on policy work is really to support the presence of biochar into the European policy framework. Specifically today, of course, I'm gonna talk about sewage sludge biochar because one of our goal is to see this feedstock included for biochar into the EU policies and initiatives. And this is, of course, a waste stream that has been more and more discussed for its great value. And of course, now it's one of the central themes of the EBI work on policy. So a little bit of background, what we already have on the table. So when it comes to sewage sludge as a feedstock for biochar, we can count on many achievements. First of all, the scientific basis. So composed by literature and researchers from all over the world have been really developing rapidly during the last years. And this also thanks to the high, no, the one before? Yeah, okay. This also thanks to the high technology readiness level. I don't know why it insists. It just wants me to get over this, but okay. Yes. And so also thanks to this high technologies readiness level, we have we already have the market potential for a waste source, a concerning waste source for all over the world. But how European policies and initiatives will reflect this potential is still blurred. And this is when the EBI, where the EBI takes action. So not everything, of course, is bad. We want to remind you that last year, the fertilizing product regulation included biochar into the CMC 14, and a lot of member states regulation, like different member states regulations, are allowing sewage sludge biochar for land application. And also non-plant-based biochar are being discussed for land use, for a regulated land use. So even though, yeah, so even though sewage sludge is not included in the positive list of feedstock for biochar, the discussion is definitely open. And also the surrounding policies we have in the European Union now are okay. So the surrounding policies are changing, like talking about agriculture, nutrients, and urban wastewater treatment. We are really seeing the landscape changing, and this opens new opportunities and new space for intervention for biochar from sewage sludge. So here I'm going to present you very quickly some of the EBI activities. Our key word, of course, is cooperation. We collaborate with the scientific institutes, universities. We continuously interact with our members through, for example, working groups. And also we can count on cooperation with other platforms such as the European Sustainable Phosphorus Platform, which has been advocating for the phosphorus recovery for many years now at the European level. This is just, okay, well, okay. So talking about our activities, we just released on the 31st of January of this year the position paper on. This is really okay. Let's see if it's just my movement. Okay, so here we have like the updated position paper on sewage sludge biochar. This is a product of our working group on sewage sludge carbonization, and our call was specifically on the inclusion of biochar from sewage sludge into the FPR. So the main concern of the JRC when they published their evaluation was, of course, the safety of biochar, so pollutants removal. That's why in this position paper that you can download very quickly before it changes again with the QR code, is like wants to summarize like some of the most recent literature pieces on pollutant removals, and of course also on sewage sludge biochar, and it's just off, some special effects. So also about the sewage sludge biochar properties as a pH fertilizer and as a carbon removal solution. So you can find it here or on our website. And lastly, I would like to remind you how much the EBI is counting on communication to change the policy framework, the European policy framework, because really communication and interaction with people leads to changes, and policymakers need to know what is already there with biochar from sewage sludge and biochar in general. So the more we tell the story about what is at the same time a solution to many issues and a source of value for Europe, the more this story will be heard. And talking about biochar story and telling the biochar story, we invite you to join us on our Biochar Summit, which will be held this summer in June in Helsingborg. So just visit our website of the event, and I hope to see you all there. And yeah, now I leave the floor to Helmut from Pyreg. Thank you very much for listening to me and for all this a little bit messy presentation, but thank you. Thank you.
Yeah, thanks. So thanks a lot, Donata. And now I have the pleasure to present our first presenter here. Is Helmut Gerber, one of the really the pioneers in biochar and carbonization. One of the first ones who had a plant running, and he also is definitely in Europe the pioneer of biochar carbonization, or like sewage sludge carbonization, I would say, having lots of experience with municipalities, with different legislations, getting it into the system. And now I think we are on a stage where we can maybe finally get where he tried to be in the last 10 years or so. So thanks a lot. Please, Helmut.
Yeah, thank you, Harald. After just falling off the stage. Yeah, very short introduction into Pyreg. So I personally started 1999 with gasification, switched to pyrolysis in 2003, did a lot of research at the university and founded out Pyreg out of this research project in 2009. We are almost 100 employees now and building machines in 3 continents at the moment. We try this. No. Yeah, now it works. I think this is quite common knowledge. Everyone knows that we need carbon negative technologies to generate this effect, so we can save carbon dioxide emissions by not burning fossil fuels and so on. But to reach the path into 1.5 degrees or even 2 degrees, we have to have carbon negative technologies. And biochar is one of these technologies. So you have direct air capture and so on, but the biochar is also now, or the last years, accepted by the IPCC panel as carbon negative, and that's the area where we are working in. The effect is the following. You have the photosynthesis, so the plants are capturing the carbon dioxide. Carbon dioxide will be as carbon part of the plant. If you don't burn the plant, if you put it into a pyrolysis plant, and this can be any pyrolysis plant, that doesn't have to be a Pyreg plant, you create carbon. This carbon is very stable, it's permanent in the soil, and we will hear something about this from Paal later, about the persistence of carbon in the soil. So it's very stable. It's like more than 1,000 years. And you can use it as a soil conditioner, or if you use it in building materials like concrete, that's very obvious, it will be stable there also. If the material is used in the soil, there are some side effects to the carbon dioxide removal. So you can see this is a meta study from led by Hans-Peter Schmidt, Claudia Kammann, and others. And they reviewed 26 other studies, so that's really the grand mean of these studies. And you can see there are a lot of fields where biochar helps in the soil, like crop yield and water use efficiency, water holding capacity, and so on. And there are some effects where it also helps, like nitrogen leaching. So it's a very good material, and traditional is used in soils to help bad soils to get more yield. Yeah, not all biochars are equal. You can change the biochar by changing the type, how you temperature, time, resistance time, and so on. And it's important, and it was shown by EBI before. There are some parameters which which are important to get some results out of it. If we switch to sewage sludge, the question is, why sewage sludge? So sewage sludge at the moment is widely used in Europe still as for agriculture uses because of the phosphorus content. And the reason why, you can see here, because there will be a peak of phosphorus. There are different studies, some talking about it's reached in the next 10 years. Maybe it's 2050, but there will be a peak of phosphorus production. And then the phosphorus sources, they are not endless. So we have to care about phosphorus, reuse and recycle it. And you can already see the prices are going up. This is something I just extracted from the internet. The phosphorus rock price from Morocco is just going up all the time. And the reason is because the rest of this phosphorus is, you can just source this in countries where it's, for political reasons, not really easy to get the hands on it. So we have to reuse and recycle phosphorus. If you put it directly in the field, the sewage sludge, it may contain organic pollutants, microplastics, and so on. And that's maybe not the best way. And I can show you that the sewage sludge biochar may be one solution to make a better phosphorus out of the sewage sludge. So this is the quality of the sewage sludge in Germany. I think it's the same in France and in other European countries. You can see that's every time the question about the pollution, the heavy metals are the main question. And we can see that the heavy metals are really heavily reduced the last 20 years or 30 years in German sewage sludges. If we pick one contamination, that's the cadmium contamination. And you make a comparison between sewage sludge and the contamination in phosphate rock in different countries. You can see the sewage sludge contains around 1 milligram of phosphorus per kilogram. And if you look to the phosphate rock, you can clearly see it contains more heavy metals. So the question about heavy metals combined with sewage sludge alone is not really okay, because different alternatives contain more cadmium. So it's a good idea to use it. Not the cadmium, but the sewage sludge. That's our process. It's divided in two main parts. It's a reactor, pyrolysis reactor, and we have a special type of burner. If you want, I don't want to bother you with the details. We have a booth there. If you want to know more about this, I will be there later. And different processes are very similar. This is the integration of a machine in a wastewater treatment plant, how we did it in different projects in Germany and also in the Czech Republic. Usually you have the digestion, you have the dewatering screw press, and then you need a dryer because the sewage sludge obviously is wet, it's more liquid. And to make pyrolysis with sewage sludge, you have to get rid of the water, and the best way to do it is to use a dryer. And then you have the mineralization or pyrolysis or carbonization, whatever word you use, and you get the phosphorus fertilizer. And the key is using the heat in different ways. So pyrolysis creates heat, the belt dryer needs heat, and the digester gas usually is used in a gas turbine. And the key factor is that the most wastewater treatment plants are off-grid. They are not lined to the city directly or to any heat line. So they usually do not have use at the wastewater treatment plant for the heat. And we can use this heat, put it in the belt dryer, and create a closed loop from the point of the energy. Yeah, coming to pollutants, one important topic is PFAS, so the per and polyfluoroalkyl substances, difficult word. We did some researches with our clients, mainly in the US, in Silicon Valley, and at the Silicon Valley wastewater treatment plant, which runs a Pyreg. And they were able to show that almost everything is gone. And we will see also new results from WOW, which Paal will show you later, that more than 90% of the PFAS is gone. It's not in the biochar, it's not in the exhaust gas, it's just converted to its elemental composition. Then we have the PAHs. We did some research on PAH reduction with polluted biomass. So we had a biomass which contained 5,000 milligrams of EPA 16 PAH, so highly polluted biomass. Put it into the machine, and we were able to reduce it to 1% of the initial PAH content. So you can clearly see that pyrolysis, if it's done right, does not create PAHs. It can reduce PAHs by converting PAHs to elemental carbon and hydrocarbons, which are burned in a combustion chamber. Then we did also research together with the German EPA, so the Umweltbundesamt, about pharmaceuticals, which the research was done at a full-scale plant in Germany, in Unkel, 2019. And they were able to clearly show that all these pharmaceuticals were gone. So they were able to prove that they're in the sewage sludge, they're everywhere. But when the material enters the pyrolysis, the temperatures and the time just destroys these pharmaceuticals. We did also research on dioxin. We took dioxin polluted biomass from the riverbanks of the river Elbe. You know, this was ancient Eastern Germany. This area, the soil there in the banks of the river is highly polluted with dioxin, and the biomass also. And we took this biomass, which had a soil pollution about 250 nanograms per kilogram. And the dioxin after pyrolysis was reduced by 95%. Also the same reason, treatment with the temperature and time. And this material, its organic pollutant, is destroyed. Then we have again the topic cadmium, which is also very important all the time. We can see that higher reactor temperatures are evaporating the cadmium. So if the temperature is higher than 500 degrees, cadmium will be evaporated in the pyrolysis gas, passes the combustion chamber, and you have to filter it out later with an activated carbon filter, which we do. The problem is usually if the higher the temperature gets, the more unavailable the phosphorus gets for the plants. And this you can see in the columns. We have different temperatures, so 500, 600, 700 degrees. And the hotter the phosphorus gets in the pyrolysis, and you compare it to triple superphosphate fertilizers, the lower the availability for the plant is. So there's a trade-off. It's not the best to make it as hot as you can because you lose phosphorus availability. And usually you do not need these high temperatures to get with your cadmium content below the limits of the European fertilizer legislation. Yeah, the last fertilization trials we did were last year. They were run by the state of Hessen in Germany. And you can see that if you compare the carbonisate made from sewage sludge and compare to triple superphosphate, which is let's say the standard for fertilization, you can see it's in the same area. So it's like 80% of the value of the fertilizer which you can buy, and the prices are highly different because fertilizer at the moment sells around 600 euros a ton, and we are talking about a material which you can get almost for free because it's traded as a waste. Yeah, my conclusion for sewage sludge biochar after doing plant trials and so on starting 2008. So in no instance municipal sewage sludge exceeded the limits of German fertilizer legislation. It's very easy if you see the sewage sludge and you know the mass conversion of the different materials, if you have an analysis of the sewage sludge, you can directly tell people it works, it will hold the limits of the fertilizer legislation or not, and in most cases it will hold the limits. Sewage sludge has a significant phosphate fertilizing effect if the temperature is not too high. So in our experience, below 700 degrees and higher than 500 degrees, which is needed to destroy organic pollutants, is a good temperature. And there's the conflict between phosphorus availability and cadmium reduction. So if there is a lot of cadmium in the sludge, you might want to have a higher temperature, but you have to think about that your availability of the phosphate is going down. One thing is very obvious, nitrogen is lost during pyrolysis. Not everything, but up to 60–80% of nitrogen is lost. In some cases, this is an advantage because, especially in northern Germany and Netherlands and so on, there are high nitrogen pools and they have problems about nitrogen. The ratio between phosphorus content and nutrients stays the same. So if you put sewage sludge on a field or carbonate on a field, you don't put more heavy metals anywhere. Yeah, so that's more or less my outcome. Harald is just showing I'm out of time, running out of time. So I want to come just for one important last topic, and that's the question about carbon negative emissions from sewage sludge carbonate. So if you use the triple superphosphate or anything else, which is the typical fertilizer, you create 1.5 kilogram of carbon dioxide emissions just by producing this material per kilogram of phosphorus pentoxide. If you use any time of biochar, sewage sludge biochar carbonate, this material has a negative global warming potential from minus 4.01 kilograms. So there's a huge difference in the carbon dioxide negativity from the biochar, which is very obvious, comes with the carbon. I have just put the calculation behind. If you're interested, I can explain it. I will skip this. And if you see it in just a diagram, you can see it's clearly below everything else. And this is not only Pyreg, this can count for any type of biochar. We took our example here. And thank you. I try not to fall off the stage now.
There's stairs. As it is all black, we didn't see that there are stairs. So thanks a lot, Helmut. That was a wonderful presentation. I think it also kind of showed the scope of what we're working on regarding this topic, from elimination of pollutants, actually, because we're using sewage sludge on fields now, just as a pure product. So we can handle the problematic issues of it. Through carbonization, we have full chemical compliance with fertilizing products regulations, which also I think is interesting, just because it's made from sewage sludge and people don't really get the chemical transformation of this material. It is an issue that has to be discussed quite intensively. And we also saw the carbon balance, which is super attractive. So we've seen this from one technology now. Now I would like to invite Christian Wied from AquaGreen on stage. They're also here present. And they have a rather a bit newer technology, like a more recent tech company. And they're also working on a very interesting system of sewage sludge carbonization. Thank you, Christian.
Thank you. So I will focus on PFAS removal and sludge management by our new fully automated sludge drying and pyrolysis system. So AquaGreen is a clean tech company from Denmark. We have invented, you could say, the a new system which is integrating the sludge drying and the pyrolysis in the system you can see here, which is in operation in Denmark. Having the system integrated means that we can run a continuous process, which is also fully automated. So the operators do not need to know how to operate a complicated system. They have to push a start and a stop button to operate it. The dryer is the complicated part. It's developed specifically for drying wastewater sludge and cuts the sludge up in small pieces so that it's ideal for the subsequent pyrolysis. When you look at the system, you have the dryer to the left, you have the pyrolysis oven in the middle, and you have a burner for incinerating all the pyrolysis gas to the right. I'll show you a video just shortly. So the key here is that we are burning all the pyrolysis gases. We do not have any bio oil or any tars. We keep the pyrolysis gas hot. We burn all the gases to generate the heat that drive the whole process. The heat is coming from the sludge itself. So we get the sludge drying for free. We are not using any external energy for the drying. The flue gas from the incineration is heating the pyrolysis, and we also use the flue gas for heating the dryer. And in the end, we recover around 70–80% of the heat as hot water because we condensate the steam that is generated from the sludge, all in a continuous process. The system is treating sludge from around 50,000 people, so it's very well suited for mid-size wastewater treatment plants. We are not covering million inhabitant cities, but we are covering roughly 50% of all wastewater treatment plants in Europe. You have an 8 to 10%, 10 times mass reduction, so you are saving a lot on sludge handling cost. And we also, with the system here, we are generating 2 gigawatt hours of hot water annually. Will you turn on the video? So we'll just show a short video from the system in operation in Denmark.
Forvile wastewater treatment plant is located in beautiful Odsher, northwest of Copenhagen. The world's first integrated steam drying and pyrolysis plant upcycles sludge from 50,000 people. The plant converts sewage sludge into biochar and district heating. It protects the groundwater as harmful pollutants are removed. The plant protects the climate as biochar captures and stores CO2. The container empties the sludge onto a conveyor. The sewage sludge contains 75% water when it is loaded into the steam dryer. After 2 hours, by use of superheated steam at 200 degrees Celsius, nearly all water has evaporated. The dried sludge is conveyed to the pyrolysis in a closed and fully integrated process. The energy from the sludge is regained. First, it is used for the pyrolysis process, then for the steam drying process, and last, for local or district heating. The pyrolysis operates at 650 degrees Celsius. The flue gas is cleaned in a scrubber. The pump on top of the condenser sends fumes to the burner. This eliminates any malodor. In the burner, pyrolysis gases are incinerated at 900 to 1000 degrees Celsius. The plant is fully automated. Every part of the process is monitored real-time. The hygienized, odorless biochar contains around 30% carbon and 6% phosphorus. Harmful pollutants like PFAS, medical residues, and PAH compounds are eliminated. One plant saves 3,500 tons of CO2 per year and protects our drinking water. The AquaGreen Hekla technology, sustainable biomass treatment for a greener future.
So as mentioned by Harald and by Donata, one of the key elements of getting biosolids biochar accepted as a fertilizer is to be able to prove that we eliminate organic contaminants. And as well as you've seen from Pyreg, we at AquaGreen have also shown that pyrolyzing at 650 degrees C for 20 minutes, as we do, is eliminating all the organic compounds that we are detecting in the sludge. So here you see a slide showing that all the PFAS we have in the sludge cannot be detected in the biochar, nor in the flue gas, or in the technical waters coming out. Likely, or in the same manner, we also see that we eliminate all the pharmaceuticals we can measure, also the pesticides we see in the sludge, as well as, for example, PAH compounds are all not detected in the biochar. So we have a system which is extremely efficient in removing all organic pollutants, and we should have a green pathway for getting it approved as a fertilizer, we believe. From a climate point of view, we also, it's clear we store the carbon in the biochar. In our plant's perspective, we store around 500 tons of CO2 in the biochar. But on top of that, we're actually also eliminating the CO2 emissions from the sludge. It's typically today stored for 6 months and then applied on farmland. And when we look at the LCA done by the Technical University in Denmark, we can see that we are saving around 2,000 tons of CO2 emissions pyrolyzing the sludge instead of spreading it on farmlands. On top of that, the 2 gigawatt hours of hot water that we generate can be used for local heating for the anaerobic digestion, can be used for district heating. That is also replacing up to 1,500 tons of CO2 if you compare to heating with fossil fuels. And we also reduce the transportation around 10 times when we look at reducing the sludge volume to the biochar. From a cost point of view, this is actually an application which is very advantageous. The sludge handling cost in Europe today varies between 50 to 200 euro per ton. Once we are at around 50 euro per ton or higher, we have a positive business case on top of the environmental and climate benefits. So with this system, we are typically looking at a return of investment from 3 to 7 years. We have various incomes that are not seen before we save on the sludge handling, but we also get new income from the carbon removal credits from the biochar, and we get new income from selling the biochar, as well as potentially selling the heat for district heating. In Denmark now, the Biosolids biochar is sold at 100 euro per ton. So, and that is because the biochar is seen as a valuable resource. On top of what Helmut showed on the phosphorus fertilizer perspective, the water holding capacity is also hugely important. If you consider the drought we had in Europe this past year, we have so in Denmark we have been able to convince the authorities, the Danish EPA, that biosolids biochar can be applied to soil as long as we meet the requirement that we pyrolyze at 500 degrees C or above for more than 3 minutes. Then the Danish EPA accepts the documentation, the scientific evidence that the organic contaminants are removed. And having that, then we have an excellent fertilizer or an excellent soil improver. And here on top of, you could say, the 30 trials that Pyreg has done, I just show you a short example of results on the water holding capacity. So when you add, if you take these Chinese cabbage pot trials, if you add from 0 to 3% biochar in the soil, you're tripling the the soil water content. So we go from having a soil with 10% water to a soil with 30% water by adding 3% biosolids biochar to the soil. And this really has, you could say, a huge potential when we're looking at water-depleted soils under drought conditions. We also see, as like what Helmut showed, we see that the phosphorus content is available for the plants. Here we are measuring the phosphorus content inside plant tissue, which is also here increasing with 60% when we are adding biochar from biosolids to the soil. So some examples of trials that underline the soil improving and the fertilizing effects of biosolids biochar. We have a booth at the Danish Pavilion in G30. Thank you a lot for your attention. We look forward to talking to all of you that are interested. And you have my contact details here as well.
Thank you, Christian. Very interesting presentation, and I think it's wonderful to see how the different trials of different companies are adding up to creating a wonderful closed picture, and we're gaining more insights and intelligence on what we can do with this set of technologies. So the next presenter will be Daniela Meitner from NGE, and she will present on a topic that we haven't touched yet, another pollutant which is highly relevant in sewage sludge, and also on the scaling, rather on the small scale of technologies, because we also have to think of different sizes of municipalities, and we need to treat sludges in different quantities. So this will be your part. Thanks.
Thank you, Harald. Also today I'm presenting our Pyro3 system. It's on our mind a revolution in sewage sludge conversion. Here you see the Pyro3 system. Like AquaGreen, we have also a combination of drying unit and then the pyrolysis. For example, when we are using sludge with around 20 to 25% of dry matter, it is going into the vessel. Via a screw, it is brought to the drying. There it is dried up to 80 to 85%. To make the handling of the material a little bit easier, we are pelletizing the sludge. These pellets are going then directly in the pyrolysis unit. The exhausting gas via the pyrolysis is then burned directly at the end of the pyrolysis chamber. We are using there the temperature for the pyrolysis itself and also for the drying unit. So the whole system don't need any external thermal energy. For example, when you bringing in 5,000 tons of sewage sludge per year, you can create 675 tons of carbonisate, which means that we can approximately save 540 tons of CO2. As Harald mentioned, we are able to have a really modular system, which has a compact, it is also really compact. We have three different sizes of our units with our Pyro3 1500, which has an annual throughput of from 740 to 1,400 tons per year. Then the Pyro3 3000 for processing 1,500 to 2,500 tons per year, and the biggest unit with 5,000, Pyro3 5000 for 3,000 to 5,000 tons per year. When you for example, when you have a wastewater treatment plant, which we need have more sludge, then we are engineering multi-line systems. In the next slides, I will show you some example of different plants. Here you see the Pyreg 3000. It was our first plant which was constructed. It is a line concept where we have the drying unit and then going in one line to the pyrolysis unit. This construction can be installed like your with how you have place in your wastewater treatment plant. There are two more examples. On the left-hand side, we have a double-line Pyreg 5000 for handling 10,000 tons of sewage sludge per year. And right now, we are engineering a multi-line system where we are able to handle 30,000 to 35,000 tons per year. And there we are installing 6 drying units with 4 pyrolysis units. So I just pick out some of the highlights of our system. We have really complete treatment, drying and thermal treatment of dewatering sewage sludge to an intermediate or final product in the most compact, fully automatic and energy efficient form. It is a modular design. We are able, the utilization of the process engineering synergies in the area of exhaust air purification. The dryer simultaneously function as a flue gas purifier with chemical separation of CO2 by reaction for existing NH3 from the drying process. As we already heard from our partners, we are able to remove PAH or PFAS. And now I want to focus my talk on microplastics. Before we can speak about the removal of microplastics, we have to think about how many microplastics we will find in the sewage sludge. For that, I will reference on a study from the Austrian Federal Environmental Agency. There they have a look on 35 wastewater treatment plants with different sizes. The size was from 5,000 to 500,000 per people equivalent. Different analyze methods were used, but for me, the biggest fact is that we can find nearly 85,000 pieces of microplastic in 1 kilogram of sewage sludge. And they have a size of 0.5 to 1 millimeter per piece. What will be the factors of microplastic in the sewage sludge? Of course, we have different size of wastewater treatment plants. We have different locations. We have, on the one hand, the treatment plants from the cities, and on the other hand, from the countrysides. And what they said in the study, the most influencing factor is the surrounding industry, like recycling industry, the food industry, and also the chemical industry. In the sewage sludge, the most common plastic types were found, like polyethylene, polypropylene, PET, polyurethane, and polystyrol. And you can find in many literature that it will be removed at a temperature higher than 500 degrees. Just to tell you something why I can say that in that way, we are also doing pyrolysis for plastic residues, and there we see that at the temperature 400 degrees, the plastic is going in the gas phase easily. So I hope I am in time, and thank you very much for your attention.
Thanks a lot, Daniela. So now we've kind of completed the picture of pollutants, or does anybody know of others that we didn't mention yet? Okay, happy about that at least. We also saw that there are modular systems. We have smaller units, which Daniela presented. We have the intermediate ones, scalable also in different directions. And now I would like to invite Paal NILSEN from WOW, just behind there, to show us how we can scale into the larger direction and with different types of systems. And he will also elaborate. Oh, yeah.
Okay, thank you, Harald.
On other topics, yeah, like climate and also elimination of certain pollutants.
All the good
Thanks.
stuff about biochar, I guess. Thank you so much for having me. I'm happy to be here. Coming from WOW, we have a booth just behind you, so any questions after my presentation, happy to address them. WOW is a Norwegian company on the Norwegian Stock Exchange. We come from cruise ships, do all sort of wastewater, waste management on cruise ships. And now we have even put up pyrolysis on the cruise ship. And then, luckily, we were able to join forces with the ETIA, French company, on pyrolysis. They have this BioGreen technology, which is very welcomed into our family. And the last part of our family was C.H. Evensen, a Norwegian company excelling in industrial heating applications, oven and so on. And they have a nice rotary drum type of pyrolysis technology that we also now have in our portfolio and as a family. Last but not the least, we have also a daughter company, WOW Green Metals, which is building factories now for biocarbon for the metallurgic industry. So, the smallest unit we have is a microwave-assisted pyrolysis system, which we now have put into the biggest cruise ship in the world. It will start sailing this autumn. And in there, we will produce 1 ton of biochar per day from wastewater, from sewage sludge and food waste. So you can see the microwave gate coming into the reactor, and then you have the biochar transported out, and it comes out in the back end there. You can see the happy crowd on the test facility taking the nice biochar off. Typically, a passenger will, in a week cruise, produce 5 kilos of biochar. So he can buy that in the tax-free shop. The French technology that we pursue is the BioGreen system, which is an electrically heated screw conveyor that has a very precise and good process control. We are able to really control the process accurately and produce beautiful biochars with this. So this has a wide applications. Come to some examples. And Eric Pellerin will also talk about this technology in specifically tomorrow regarding circular economy. So the new machine we are building now is a rotary drum machine. This machine would typically take 100 ton dry solids a day. So it will produce like some 8,000 ton of biochar per year per machine. You can see the guys there in the workshop. We have a workshop in Fredrikstad, south of Oslo, where we put this together. 2 weeks ago, I was inside the combustion chamber. You could see on the drawing there. So it will be due this summer. very exciting for us. Here we can combine pyrolysis gases and electricity as a heating source. And this is typically an energy flow of this. So we could scrub the pyrolysis gases, take off the oil if we like for other purposes, or we can use it for thermal benefits. So it's an indication of how this works. So to sewage sludge, ETIA and the BioGreen system has been in operation in Japan for many years now, together with Kobelco. We have worked on sewage sludge there for that moment as a fuel for the coal-fired power plants. But after some pretty heavy approval processes, I'm happy to say that the Japanese Sewage Works Agency now has finally approved our technology for use in Japan for sewage sludge, and they even promote it on their homepage. So that's a good news for us. It's a long, heavy work, and now we are developing more projects in Japan, since they also come to realize that phosphor is a precious material they need to recycle and not only combust. Okay, in WOW we have a very big development group, 17 people in Oslo, many people in France. We are doing a lot of work on valorization of waste. And you could see we have a very good cooperation with the Norwegian Geotechnical Institute and the Professor Gerhard Cornelissen, and done a lot of work on pyrolysis of these waste streams. Down in the bottom, you can see Gudny Flatabø. She is our PhD student, working specifically on using the pyrolysis gases and condensates into anaerobic digestion for making biomethane, to make the combination of anaerobic digestion and pyrolysis the most efficient. We have a test rig where we have done a lot of exciting tests. And today I will just complement the previous speakers with some of our latest results on the overall mass balances of PFAS through the pyrolysis. I think by now everyone agrees that pyrolysis could destroy PFAS, but it must be done right. And I'm not sure 3 minutes and 500 degrees, as Danish authorities says, is always good enough. But this is typically what we can get. And I'm happy to see some PFAS in the residues rather than zero, because then I don't trust the measuring techniques. So there are some traces, both in the char and in the flue gas and so on, but they are controllable and small. And if we process them the right way, we have a control. Another interesting topic is also to make the biochar a sorbent for the same pollutant that you eliminate. And this is an example where we took sludge from the local wastewater treatment plant at Oslo Airport. That is one of the sludges with the highest PFAS contents in Norway. And we made a pyrolysis out of it. And as you could see from the previous, maybe I can stop, yeah, the previous slide. So you will see that this biochar here is eliminated all the PFAS there. But when we blend 1% of that biochar from the sewage sludge works at the airport with the soil in the vicinity of that wastewater treatment plant at the airport, because the soil is very polluted with PFAS from firefighting foams and what have you. So we brought 1% of the char from the sewage sludge into the soil from the Oslo airport, and then we measured the leachate of PFAS from that soil. And the good thing, the good story, otherwise I wouldn't tell it, but the good story is that if you have the right char and you process it right, you could almost eliminate all leaching of PFAS from the PFAS contaminated soil in question. So this shows activated biochar, which is the best, but the sludge number 3 is actually the sludge from biochar, sludge from the wastewater treatment plant. And you could say we could eliminate up to 98% of the PFAS, depending on the molecular size of the PFAS components and so on. But it is comparable to the activated biochars. Very promising. And this is with as little as 1% blend into this. So we have a story to tell the local wastewater treatment plant there. Yesterday, this is just out of the press. Yesterday, the countries Denmark, Sweden, Norway, the Netherlands, and Germany joined forces into the EU and put forward this system. It was announced at Reuters yesterday to ban PFAS altogether. And why? Because it is a forever chemical that comes with a lot of health costs. I think I read an article about associated health costs in the US due to PFAS equal to some $5 billion a year. It's all sort of diseases you could get from that. So to eliminate it and to have one end of waste process like pyrolysis, I think is crucial. So to do pyrolysis with AD, I think it makes sense to combine it with anaerobic digestion. Most of the wastewater treatment plants do biosolids reduction through anaerobic digestion. What we have seen at to pyrolyze, we need to dry, and to dry, we need to remove water. We can remove water more efficient by doing thermal hydrolysis. What we do, we cook the sludge to elevated temperatures and then dewater at high temperature. This is just some different sludges where we have treated the sludge at 170 degrees and then done some thermal disintegration with steam explosion and then dewater it. And you could see that we could almost double the dry solids in the sludge after this process. So we build these type of thermal hydrolysis processes. We have already put that also into the cruise ships to reduce the need for drying on board the ship. And as you could see, this is actually the digesters from the sewage sludge plant at the Oslo airport. But there you could see we could treat it and we can get 50% dry solids of the sludge coming directly out of the centrifuge. There is reducing the need for drying by almost 50%. So this is our take on how we could do energy efficient processes with pyrolysis in the future. And as Helmut says, some of the nitrogen is removed. We could capture some of it in the condensate and bring it also for digestion and into a nutrient sterilized or pathogen-free type of flow. So we are doing all sort of these anaerobic digestion tests with the pyrolysis condensates to see how we convert them also to methane. And Gudny has now shown that adding the amount of condensate coming out of the pyrolysis of the sewage sludge, if you bring that back to the digester, we can get the same methanization as for the original sludge, which is a good thing. So to the scaling, I think if you use the BioGreen machines like you see on the left, you see a two-line system that is suitable for 200,000 people. This is our standard machine taking a ton of dry solids an hour. And then for the larger machines, one of these machines could do sludge worth of up to 2 million people. So also to address these type of technologies to the larger wastewater treatment plants, I think is crucial. And now we will put forward the machinery to do so. And then, of course, we plan with the industrial partners now to look at much bigger projects for the metallurgic industry, for the thermal energy needed for industrial processes. So these machines, as I said, could do 8,000 tons biocarbon a year each. And we are looking now at projects like this. I will end my talk with a small quiz. And the quiz would be on permanence on biochar. EBI with Harald has made an effort to document the permanency of permanence of biochar. It's been 100 years, 1,000 years, 2,000 years, whatever, but maybe it's even more. So there has been studies that will be published at Helsingborg Biochar Summit with all the details on the permanence of biochar, which is very optimistic for our community. And then the question would be, which is 2 week old and which is 290 million year old? This oldest is a biocarbon found in the crust of the soil in Australia. So the carbon is the same, the structure is the same, so why shouldn't the permanence be the same? And if you get the right answer, I think I have a prize, which is about 290 million year permanence. Okay, Harald will judge who is counting the right. Okay, see you in Helsingborg. Thank you.
Yeah, so I got a prize here. Thanks a lot for this encouraging presentation. We can scale. We have lots of synergies, and I think that's the part where it gets really interesting. Not only the production process and the product that we have, but also stating the persistence of this product, but then making use of it, like for example in soil remediation. Drastically reducing the leaching of those toxic, difficult substances that we can also eliminate through the process of pyrolysis. So connecting the dots, that's what we will do also at in our Congress in Helsingborg, of course. We don't have the time, we just only could scratch the surface, but I hope that was a valuable input already. Now now you don't see it anymore, maybe you might remember. Which one was the oldest one, the left one or the one to the right? Now, so if you want to raise your hands for the one to the left. Yeah, and the other ones for the right. It's kind of equal. I mean, many people don't seem to have an opinion, and it actually, I wouldn't say it matters too much, because that we have the same structured material, and actually we're not using this technology, just having a microscopic view of it, but state-of-the-art technology that's used in geochemistry to analyze the difference or similarities, and it seems to be very interesting. So this is for generally the biochar world, like a great step. I don't know who I will give this to. But I think, yeah, you can have it, and then the rest might find some more behind you. I can take maybe a question or two, because we have 8 minutes actually until we are kicked out here. Yes, Susanne?
Yeah. Thank you so much, Harald. I'm Susanne, the chair of the German Biochar Association. What I was thinking about is, because we have this hard legal regulation about using the biochar from sewage sludge, if there would be an opportunity to buy it to Denmark, because I think they are allowed to use it, and perhaps bring it back in this way to Germany, or what could we do? Because we have so much advantages, but we are not allowed to use it.
I could try to answer, but my answers depend on mainly the input of Helmut. I might give him the microphone there.
Yes, that's a very good idea. So we did it to Sweden, because in Sweden it's legal. And the wastewater treatment plant in Germany was brought to court because they cannot transport waste over the border, even if in one side it's a product and a fertilizer, and then on the other side of the border, the German side, it's a waste. And we are working together with the authorities to sort it out, because there should only be one European law. But in fact, at the moment, it's a little bit difficult.
So there is no chance for sewage sludge converted into biochar from German plants, actually.
Our lawyer says yes, it's legal. So, but the Ministry of Environment in my state sees it different. So there is still some differences in the opinions. I think it's legal, but you can try it and check what happens.
Yes, so actually, it should be legal because you can't really forbid something in one European country and then permit it in another. So because it would hinder the competition in between countries. But if a national state hinders you in doing something, you can go to court, but that's long processes, and that's basically the problem. So as EBI, I can say we're fighting this at another level. We're trying to get it into the fertilizing products regulation. And that might be the case earlier with certain other materials like animal byproducts that can be carbonized and then sold as fertilizers. With sewage sludge, it's a bit of a longer approach, but I think at the moment options are opening up again. So things are changing dramatically, and it's also due to our work, but also due to the general understanding of carbon sinks, the necessity of carbon sinks, and also the product biochar, which has been unknown. And now, basically, if you come talk to people, at least they have heard of it, even though they don't necessarily know what exactly it can do. But that's even the case for us, right? Who consider ourselves rather experts. Do I have another question? We have 5 minutes left. Yeah, okay. We can even have a few more minutes more. So thanks to the IBI. I should have asked differently. Who still feels after all this input capable of posing a question? Yes, please.
Hi. So given that all this biochar has not been able to be used as fertilizer, what has been done by those companies with this biochar, all the biochar they produced till now? What's the market?
Well, it's illegal to be used in certain countries. It's just not all over Europe. But maybe Christian wants to answer.
In Denmark, our first client is selling the biochar to a company that is making urban planting solutions. And part of the urban planting solutions for planting trees in urban cities and parks, they are also selling the soil, guaranteeing a certain growth of the trees for the next 10 years. And part of that soil solution is including biosolids, biochar. So there's also a lot of experience from Sweden using biochar in such solutions, ensuring, you could say, the water holding capacity and ensuring the long-term fertilization. So there's quite a lot of interest in this in Denmark and Sweden. And we are also, so it's still country dependent to get the approvals. And that's why we are working both at a country level, but also together with EBI at a European level.
Thank you. Susanna, you wanted to add something?
Yeah, even if it's a shame we cannot use it in Germany. We had a request from Saudi Arabia. They need a lot of soil for rooftop greenings, yeah, and therefore the sewage sludge biochar would be perfect. And I know that there are some deals are going on, but it would be much better to use it in Germany. This is our aim, that we want to reach it and to get the politicians to sense, and also the wise old men which are counseling German fertilizer ministry. So yeah, because we cannot ship this good material all over the world to make soils everywhere fruitful. Yeah, we have to bring them the plants to do it from their own sludge.
Exactly. Even though we ship phosphorus all over the world, all across the world, it would be a lot more valuable to create regional and local resource streams and flows. And I heard of, for example, with Bellona, we've been talking about the screening the Sahara Desert project, and they dramatically lack resources for doing it. The sludge is something that's always available if you have a sewage system, and it's treated as a waste and it's discharged somewhere, and it's always problematic. So that's the first resource you could just hop onto, turn it into something very useful, and then start agriculture, especially with all the other qualities like water holding capacity and so on. So there's a lot of possibilities in this material.
Maybe I can add that with our customer in the Czech Republic, we were able to get the permission in the Czech Republic after 2 years. In Sweden, it needed, I think, 6 to 8 weeks. Denmark was also a big challenge for you, but you got it lately. And in Germany, we are in contacts for, I think it's like 6 or 7, 8 years, something like this, delivering the latest results every year again. And I think it's only a question of time. So in the USA, we have the permit. In Germany, things sometimes need a little bit longer, but I'm quite sure that we get the permit also. And Harald is working in the European Commission to get the permit. So it's a question of time.
Right, attacking from different angles, but we're getting more numerous. So this way we can also attack from different sides and build intelligence on it. I think that's the basis. Actually, they don't. I mean, people permitting intelligent solutions don't necessarily do that out of a bad mood or because they are just mean people. But sometimes they actually do have questions, and now evidence is building around what we have seen today. And as this is increasing and we have the scientific knowledge, of course, the options are opening up and people are calmer in permitting substances to this market. Any last burning questions? Not that I see so. Okay, thanks a lot. Thanks a lot for all the presentations and for the interesting discussions, for all your interest. And the presenters are available at their respective booths. We're also there. We have a small booth as EBI with our logo on, with the International Biochar Initiative and others. So I'm happy to see you there. And also, if you have general interests in biochar, because that was just a very small part of what we actually do, we're also available for a talk. Thanks a lot.